In this video, we're going to walk through solutions to these practice problems of determining the geometry around a central atom. Hopefully you've had a chance to try these on your own. So I'll spend less time in developing the Lewis dot structure for these and focus more on the geometry. So our first one, we have carbon bonded to 4 bromine atoms. And this is going to give us a structure that looks like this. We'll have all 4 bromine bonded to the carbon. Bromine has 7 valence electrons and carbon has 4. So bromine's going to want 1 bond to satisfy its octet rule, and carbon's going to need 4. And so these will each bond to the carbon and to satisfy the octet rule for all of the atoms. All right, there we go. So now looking at this, I need to determine the geometry. And I'll always be determining the geometry for a central atom. But what I mean by central atom is any atom that has more than one thing bonded to it, so 2 or more other atoms. Each of our bromine only have a bond to 1 other atom, and so there's no geometry to determine for them. If anything, I guess it's linear. So my carbon, I'm going to come in and evaluate this. Right off the bat, I can see it has 4 bonded atoms to it. And it has no lone pairs. So the total number of things that can repel one another around that carbon is 4. Now, it's important to point out, I think, that I'm not taking into account the lone pairs here. The lone pairs on atoms not on the central atom don't have an effect on the geometry that forms around that central atom. So with 4 things around it, it'll take on a tetrahedral arrangement of 109.5 degrees. And since none of these are lone pairs, I can just name that geometry based on these 4 bonded atoms. So this will have a tetrahedral geometry. All of these bond angles will be 109.5. If I wanted to draw it in 3 dimensions, I could. I would use that wedge to come out of the plane and dash to go back, and a bromine at each of these points here. And I still include my lone pairs even now, so they're not forgotten, even if it takes a while to draw them. This is 109.5 degrees. All right, that's our first one. We have a tetrahedral geometry. Next, we have pH3. Now, we've already done the Lewis dot structure for this one in a previous problem. We have our lone pair here. So now in this case, I have 1 lone pair, and I have 3 bonded atoms to my central atom. And I'm focusing here on just that phosphorus and what is connected to that phosphorus. That's a total of 4 things that'll repel. So again, they're all going to position themselves roughly 109.5 degrees apart. So that means that I could redraw this again with my wedges and dashes and have hydrogens here on the bottom. And you can draw in the lone pair here, or you can omit it. It's up to you. But this piece right here dictates my geometry rather than that lone pair. So instead of it being a tetrahedral geometry around the phosphorus, I'll call this trigonal pyramidal. Although these bond angles here are somewhere between 107 and 109.5 degrees. So I realized CH2O was actually one of the previous slides, so I apologize for the repetitiveness of it. Let's do that, and I'll throw in an extra one here. Or here. Hydrogen cyanide we can do next, too. So for my my CH2O, my carbon is double bonded to an oxygen, and I have a single bond to a hydrogen for my carbon. And there's 2 lone pairs on my oxygen. But I'm focusing on this carbon because it's my central atom with more than 1 thing bonded to it. And when I look at it, it has 0 lone pairs, and it has 3 things bonded to it for a total of 3. So now I'm going to break away from this 109.5 arrangement of my bonded atoms. And with 3 things around a central carbon, the furthest they can get is 120 degrees apart. And so in this case, I actually even have this drawn already with the geometry. They'll just be in a planar geometry, 120 degrees apart, and we call it trigonal planar. All right, let's do one more for fun. Hydrogen cyanide. So this has a fun triple bond like this. And again, I'm going to focus in on just that central carbon atom in this case. And I have 0 lone pairs. And I have 2 bonded atoms for 2 things. So I can get those even further apart than 120 degrees. They can be 180 degrees apart. So at 180 degrees apart, this would be a linear geometry around the carbon.